Hello guys, I'm Angelo Ariota, BSIT3A. Come and join me to listen the discussion of database development process.
A core aspect of software engineering is the subdivision of the development process into a series of phases or steps, each of which focuses on one aspect of the development. The collection of these steps is sometimes referred to as the Software Development Lifecycle or SDLC. The software product moves through this lifecycle, sometimes repeatedly as it is refined or redeveloped, until it is finally retired from use. Ideally, each phase in the life cycle can be checked for correctness before moving on to the next phase. Software Development Lifecycle Waterfall. Let us start with an overview of the waterfall model, such as you will find in most software engineering textbooks. This waterfall illustrates a general waterfall model that could apply to any computer system development. It shows the process as a strict sequence of steps where the output of one step is the input to the next, and all of one step has to be completed before moving on to the next. We can use the waterfall process as a means of identifying the tasks that are required, together with the input and output for each activity. What is important is the scope of the activities, which can be summarized as follows. Establishing requirements involves consultation with and agreement among stakeholders about what they want from a system, expressed as a statement of requirements. Analysis starts by considering the statement of requirements and finishes by producing a system specification. The specification is a formal representation of what a system should do, expressed in terms that are independent of how it may be realized. Design begins with a system specification, produces design documents, and provides a detailed description of how a system should be constructed. Implementation is the construction of a computer system according to a given design document, and taking into account the environment in which the system will be operating, example, specific hardware or software available for the development. Implementation may be staged, usually with an initial system that can be validated and tested before a final system is released for use. Testing compares the implemented system against the design documents and requirements specification and produces an acceptance report, or more usually a list of errors and bugs that require a review of the analysis, design, and implementation processes to correct. Testing is usually the task that leads to the waterfall model, iterating through the life cycle. Maintenance involves dealing with changes in the requirements or the implementation environment, bug fixing, or porting of the system to new environments. Example, migrating a system from a standalone PC to a Unix workstation or a networked environment. Since maintenance involves the analysis of the changes required, design of a solution, implementation and testing of that solution over the lifetime of a maintained software system, the waterfall lifecycle will be repeatedly revisited. Database lifecycle. We can use the waterfall cycle as the basis for a model of database development that incorporates three assumptions. We can separate the development of a database, that is, specification and creation of a schema to define data in a database, from the user processes that make use of the database. We can use the three schema architecture as a basis for distinguishing the activities associated with a schema. We can represent the constraints to enforce the semantics of the data once within a database, rather than within every user process that uses the data. The first step is requirements gathering. During this step, the database designers have to interview the customers or database users to understand the proposed system, and obtain, including documenting the data and functional requirements. The result of this step is a document that includes the detailed requirements provided by the users. Establishing requirements involves consultation with and agreement among all the users as to what persistent data they want to store, along with an agreement as to the meaning and interpretation of the data elements. The data administrator plays a key role in this process, as they overview the business, legal, and ethical issues within the organization that impact on the data requirements. The data requirements document is used to confirm the understanding of requirements with users, to make sure that it is easily understood. It should not be overly formal or highly encoded. The document should give a concise summary of all users' requirements, not just a collection of individuals' requirements, as the intention is to develop a single shared database. The requirements should not describe how the data is to be processed, but rather what the data items are, what attributes they have, what constraints apply, and the relationships that hold between the data items. Analysis. Data analysis begins with the statement of data requirements and then produces a conceptual data model. The aim of analysis is to obtain a detailed description of the data that will suit user requirements so that both high and low-level properties of data and their use are dealt with. These include properties such as the possible range of values that can be permitted for attributes. Example, in the school database example, the student course code, course title, and credit points. The conceptual data model provides a shared, formal representation of what is being communicated between clients and developers during database development. It is focused on the data in a database, irrespective of the eventual use of that data in user processes or implementation of the data in specific computer environments. Therefore, a conceptual data model is concerned with the meaning and structure of data, but not with the details affecting how they are implemented. The conceptual data model, then, is a formal representation of what data a database should contain and the constraints the data must satisfy. This should be expressed in terms that are independent of how the model may be implemented. As a result, analysis focuses on the questions. What is required, not how is it achieved? Logical design. Database design starts with a conceptual data model and produces a specification of a logical schema. This will determine the specific type of database system, network, relational, object-oriented, that is required. The relational representation is still independent of any specific DBMS. It is another conceptual data model. We can use a relational representation of the conceptual data model as input to the logical design process. The output of this stage is a detailed relational specification, the logical schema of all the tables and constraints needed to satisfy the description of the data in the conceptual data model. It is during this design activity that choices are made as to which tables are most appropriate for representing the data in a database. These choices must take into account various design criteria, including, for example, flexibility for change, control of duplication, and how best to represent the constraints. It is the tables defined by the logical schema that determine what data are stored and how they may be manipulated in the database. Database designers familiar with relational databases and SQL might be tempted to go directly to implementation after they have produced a conceptual data model. However, such a direct transformation of the relational representation to SQL tables does not necessarily result in a database that has all the desirable properties: completeness, integrity, flexibility, efficiency, and usability. A good conceptual data model is an essential first step towards a database with these properties. but that does not mean that the direct transformation to SQL tables automatically produces a good database. This first step will accurately represent the tables and constraints needed to satisfy the conceptual data model description, and so will satisfy the completeness and integrity requirements. But it may be inflexible or offer poor usability. The first design is then flexed to improve the quality of the database design. Flexing is a term that is intended to capture the simultaneous ideas of bending something for a different purpose and weakening aspects of it as it is bent. Realizing the design. After the logical design has been created, we need our database to be created according to the definitions we have produced. For an implementation with a relational DBMS, this will probably involve the use of SQL to create tables and constraints that satisfy the logical schema description and the choice of appropriate storage schema, if the DBMS permits that level of control. One way to achieve this is to write the appropriate SQL DDL statements into a file that can be executed by a DBMS, so that there is an independent record, a text file of the SQL statements defining the database. Another method is to work interactively using a database tool like SQL Server Management Studio or Microsoft Access. Whatever mechanism is used to implement the logical schema, the result is that a database with tables and constraints is defined but will contain no data for the user processes. Populating the database. After a database has been created, there are two ways of populating the tables, either from existing data or through the use of the user applications developed for the database. For some tables, there may be existing data from another database or data files. For example, in establishing a database for a hospital, you would expect that there are already some records of all the staff that have to be included in the database. Data might also be brought in from an outside agency. Address lists are frequently brought in from external companies, or produced during a large data entry task, like converting hard copy manual records into computer files can be done by a data entry agency. In such situations, the simplest approach to populate the database is to use the import and export facilities found in the DBMS. Facilities to import and export data in various standard formats are usually available. These functions are also known in some systems as loading and unloading data. Importing enables a file of data to be copied directly into a table. When data are held in a file format that is not appropriate for using the import function, then it is necessary to prepare an application program that reads in the old data, transforms them as necessary, and then inserts them into the database using SQL code specifically produced for that purpose. The transfer of large quantities of existing data into a database is referred to as a bulk load. Bulk loading of data may involve very large quantities of data being loaded, one table at a time, so you may find that there are DBMS facilities to postpone constraint checking until the end of the bulk loading. Guidelines for developing an ER diagram. Note, these are general guidelines that will assist in developing a strong basis for the actual database design, or the logical model. Document all entities discovered during the information gathering stage. Document all attributes that belong to each entity. Select a candidate and primary keys. Ensure that all non-key attributes for each entity are functionally dependent on the primary key. Develop an initial ER diagram and review it with appropriate personnel. Remember that this is an iterative process. Create new entities, tables, for multi-valued attributes and repeating groups. Incorporate these new entities, tables, in the ER diagram. Review with appropriate personnel. Verify ER modeling by normalizing tables.
So, yun guys, tapos na po ang discussion. Sana po naintindihan po natin. Thank you.